All right, it's 10 o'clock. Good morning, my name is John Shire. I'm an iOS developer with Detroit Labs here in Detroit. And this is Exploiting Swift for Fun and Profit. Now, before I get started, I'm going to mention a little bit of my own history, which is really what has influenced my desire to give this talk. I started programming Mac apps and Objective-C on the OS X public beta back in October of 2000 because it was the first operating system I'd ever used that had a free IDE that I could use. Not only that built in a compiler, but also an interface builder and all sorts of stuff like that. So my usage of Objective-C started 16 years ago. So, all of my programming experience since then has sort of been through the lens of what Objective-C could do for me. So when I had to learn Java for a computer science degree, it was, wow, this is really a lot of boilerplate, and wow, I really don't want to build UIs like this. And when I had to, and I covered a little bit of, covered Java for all of my core computer science. I covered C++ as an elective, but none of those classes really took me to the advanced reaches of those languages. Whereas my own usage of Objective-C had been able to improve, or had been able to take me further down the road of what the language was capable of, so I was much more familiar with it. So this is a quote from Chris Eidoff's and Airspeed Velocity's Advanced Swift book, which is actually a quote from another book about the Lisp language. Experienced Lisp programmers divide up their programs differently. As well as top-down design, they follow a principle which can be called bottom-up design, changing the language to suit the problem. In Lisp, you don't just write your program down toward the language, you also build the language up toward your program. As you're writing a program, you may think, I wish Lisp had such and such an operator. So you go and write it. Afterward, you realize that using the new operator would simplify the design of another part of the program and so on. Language and program evolve together. So this is really what has influenced the core of this talk is instead of the top-down design that we usually take as developers on any platform, but especially on iOS platforms and Apple platforms in general, where we dealt mainly with view controllers and then looked down the stack towards the core of the language. Instead, in Swift, we have the opportunity now to build the core of the language up towards our problem domains and be able to build code that is, because of doing it that way, more reusable, perhaps gives us better performance, and is perhaps even a little more fun to build because you don't have to deal with the big stack of stuff between you and the language. Instead, you're able to use the language directly. So what am I going to be talking about? I'm going to be talking about what was mentioned there as bottom-up architecture. And really what I call myself is type-oriented programming, which is putting functionality as close as possible to the relevant types. And because in Swift we have this ability to, especially as an Objective-C programmer, see types as real things that get passed around not only in the compiler but in the runtime, and something that's so important that it's built into the core of the language. Unlike Objective-C, where you could declare everything as ID, and the compiler would be perfectly happy with it as long as you didn't have the really pedantic warnings turned on. And at runtime, all it's doing is sending messages back and forth to particular instances of objects. And so, for the first time as a developer, I really had to consider what types I was using and how I was using them and how I was passing them around and how I can get them from one point to another in the compiler. So specifically, I'm going to be talking about Swift's generic systems, Swift's protocols, and Swift's extensions. So all of these tools enable you to build different parts of a whole that allows you to take advantage of the types that you have to use in Swift. Because like I said, for an Objective-C programmer, moving from a dynamically typed language to something that's basically statically typed at compile time was a huge change and was kind of painful. And it wasn't until I realized that these types gave me the power to do more that I really embraced this functionality. So generics, I'm not going to cover like the core syntax of what generics are. I'm sort of assuming you know what they are. But they make types and algorithms more general without the loss of efficiency. Increases our composability, reusability, and performance, although that performance at runtime comes at a cost of compile performance. It binds together types, extensions, and protocols that aren't necessarily related. You can take a type, no matter how general or specific, and add perhaps another constraint to it, and pass both of those things together as sort of a new unified thing through the type system in Swift. And this was a radically new thing for Objective-C programmers because, Objective-C had no notion of generics, and even the lightweight generics that were added for Swift interoperability are just a syntactic sugar for the compiler. It's nothing that changes the code that's generated for runtime. So this is something that in the 15 years before I'd used Swift wasn't something I'd really encountered because, like I said, the computer science program I'd gone through never really got to the point of having to talk about Java's generic system or C++'s generic system or any other language's generic system for that matter. So as part of the generic functionality, you can declare, of course, a generic function. In this case, at the top here, you see the definition of flat map for optional in the Swift standard library. And you can see that it takes a type parameter u, which is the type that the optional is wrapping, and returns that optionally to the flat map. You can also constrain these type parameters, so if you want to say that this is going to be some type, but it has to conform to a protocol or inherit from a superclass, then you would do that there. Placeholders are unlimited, but they're not variadic, so you can have as many of these placeholders as you want, but you have to define them all separately. So you're not going to be able to do something like Scala's variadic generics, where you can just say, here's a generic, start this pattern of these types of generics, and then have tu, v, w, x, y, z all defined for you as you want to use them. And it's pretty trivial to write your own generic functions. This is a function from sort of a notification center wrapper I wrote for an app that we built recently that basically takes any value type from Swift and posts it using a notification. And so you just take the type as the type parameter of any type, really, and it lets you pass that type into that function. And we can see in the standard library that they've embraced this. Swift's array, of course, is generic for the type that it contains. And you can see that as they declare this generic type now, you have this placeholder type that's declared as part of the declaration that is then available inside of the type so that you can use it for things like they use it to, when you're using subscripts, you're going to return an element, and whatever type that is whatever type that that subscript is going to return for you. And it's also going to return the slices of the same type of thing. And this gives you the ability to write types that sort of, it's not really containing other types, but use other types to their advantage. And so this is sort of going to be an example. As part of that project, I wrote a generic network operation. And it really covered multiple layers of sort of our networking and decoding stack. And this is what it looked like. Really at the base of this was going to be the Alamifier network library. If you're not familiar with it, that's fine. It's your basic asynchronous networking library for Apple platforms using NSURL session. It defines as part of its library its own result type. And this isn't something that we see in the standard library right now, but it's something that a lot of other functional languages have, and it's pretty popular. Rather than having to do something like Swift 2's try-catch, you can instead put it inside of a result enum that'll have a success or a failure. And you can see here that this type is defined with two generic properties, a value and an error. And error itself is constrained to error type. And so you have to have something that conforms to error type to be able to pass into this. And so in the success case, you return whatever type the value is. In the failure case, you return whatever type the error is. And that's as much as functionality as that goes into. So this can really contain anything that comes out of your networking stack. And so we can see through this whole chain of types and functions that we're maintaining this type information from the core of the network stack all the way up to the operation and all the way up to the view controllers that we use. And so we can see here that we have the Alamifier response serializer, which itself is also another generic type that has a value and an error. And it has to conform to the protocol response serializer type. Now, response serializer type is a protocol that defines some associated types. And I'll talk about those later on when I talk about protocols. But essentially what it gives us is for response serializer type, the one required function is something that will return a result that has a serialized object or an error object. And by doing this, we are not only able to maintain the type information from result and from the serializer, but through a protocol, and now go all the way up to now, the serialization itself, where I implement, okay, how are we going to turn this JSON into our actual types? This decodable protocol that you can see here in the generic declaration is from a library called Argo. And so Argo is a functional JSON parser, one of, 1,000 for Swift so far. And it gives you the decodable protocol unless you declare generic constraints on types, so that you can say that, in this case, my API response serializer will return a response serializer that returns this T, which is constrained to decodable and the decodable type, and my own particular error called API error. Eventually, AlamoFire will call when the request comes back. We'll call my response object function, which again has the same sort of type constraints as the serializer. And so the types that are passed from the serializer to the response method are passed with full fidelity. This takes a completion handler, which again takes a generic response, which has my type that I've already defined in my own error. And finally, I'm able to implement my own sort of wrapper operation for this. Don't ask why I had to wrap an asynchronous AlamoFire thing inside of another asynchronous thing, but it was necessary. This lets me, again, define a class that, has a type associated with it that conforms to decoded or decodable and is a subclass of operation. And as one of the properties of this network operation is the actual result all the way from the bottom of AlamoFire, which again is defined generically. And I also have an optional completion handler that can run, which again takes the result that's generic. And so we can see here that we passed a type with full fidelity from the base of the networking stack through serialization, asynchronous dispatch, and into a stored property in a class that can be accessed in the future. And this is all done using one function for serialization, one function for dispatching, one function, one class for the network operation, and the code from the AlamoFire library. So this has given me the ability to use any of our decodable types for any of these network operations and not have to define a network operation for the account, a network operation for some details of the account, another one for different types. And maintaining this fidelity also allows us in the future, if we need to do something else with these types, to be able to use that information to our advantage. So if in the future I need to come back and add another constraint on these types, I can, and not have to rewrite code from the bottom up to pass more information through. Because I have run into networking libraries that at some point say stop passing through all of the error information. And so you're sort of stuck at that layer if you want to get everything up front. So the generic system is extremely powerful, but it is limited and can have some drawbacks. You can't make things generic like you would think. Some of these limitations will be lifted with Swift 3. Some of them won't be, maybe 3.1 or maybe Swift 4. For example, if I tried to make, again, the operations library itself defines something called a repeatable. And so this was, I basically tried to build up a list of constraints on the type I was going to decode, while at the same time also defining, some other, basically a type of operation, having a superclass that itself was generic to a type that I was defining in my class definition. So, and you would get an error there called superclass constraint repeatable network operation. You cannot depend on a type parameter. And so that's another limitation that might be lifted with Swift 3, but we'll see if that actually works. So I wasn't able to create a subclass in this case. Had to go the route of like a function that would generate a generic class. One of the other things, like I said, no variadic generics. So if you ever have to, I did make things that were, here's an operation that contains 2 network operations. Here's an operation that contains 3 network operations, each with its own actual type that it was returning. But I had to do those manually. There was no way to have, just one like multiple network operation that was able to take as many types as I wanted and know what to do. You can get really bad error messages sometimes. You can run into things where the type checker in the compiler just doesn't know what to do, and so it throws up something that doesn't make any sense to you. The more you use types in Swift, the slower your compiler speed is going to be, because every time that you use a type, and especially ones that are only partially constrained or have a lot of constraints like that, is something that the type checker in the compiler has to go through and find every type in your module that could conform to this and make sure that they're all correct. Now, the standard library does define some common generic specializations, like, say, array of strings. And those are built into the standard library, so when you're compiling those things, it doesn't have to go through and generate these generic specializations as far as for optimization purposes for you. Those things are pre-built and is given a little bit of speed to you. I think that came in Swift 2.1, so people might have gotten a bit of a compile speed boost. Another thing to watch out for is that you can overgeneralize your code. And what I mean by that is there are cases in which you don't want a generic class or something like that. Because every time that you define a generic like that, you need to be able to provide type information from somewhere. Whether it's defining it in your code as the return type, whether it's, you need to create instances of a class that is generic, then it means you need to provide a type for that generic. And so it can lead to a point where, I need to do something with this generic class for this type, and then also this type, and then also this type, and then also this type. And so at some point it's like, well, maybe this shouldn't be generic. Maybe I should just have a generic function inside of this class that will transform some general type that this class has to the specific type that I want out of it. And then also there is type erasure that can be useful, so that you take in a specific type and then later on treat it as something more generic without having to, using perhaps casting or something like that, so that you don't have quite the pain that you might have through trying to take types all the way through all of your types. But that's really a case-by-case basis. The second part of this sort of architecture is the embracing of protocols. Now, protocols are something that we had in Objective-C as category, or as just protocols, I mean. And it's really a blueprint of functionality that types can conform to, or said another way, is an abstract way to define a type or requirements of types. And so these are really, one way to think of these as protocols are types that you don't really instantiate. Instead, they just define the constraints of other types. And so you would define something that, say, needs certain properties or certain methods or certain initializers. And then protocols can also have associated types, like I mentioned. And that lets us use protocols to convey type information from one point through the protocol to maybe a specific type, and then further down the chain, so that you don't lose important information along the way. So, for example, the operation library that I used was just called operations, based off of the advanced NS operation talk from last summer. But it offers a lot of functionality. One of the things it offers is the ability to just repeat any operation. And one of the things you need to do to be able to repeat your operations is conform to repeatable. And all this does is define a function called shouldRepeat that takes the number of times you've been repeated and returns a Boolean. And by conforming to this, you can determine whether you repeat your operation. This is a very simple protocol, very easy to implement. And so what I like to do, though, is I like to define for different types. Since all of my networking is generic anyway, I'll just add another constraint to that generic type that's being returned from my network stack, and make sure that it's repeatable, and make sure that if I'm, say, returning settings, if I should repeat getting settings, like if it's syncing to a database or something like that, I can check its syncing state and keep repeating until that's false, or until that's until that's false. And this lets me build sort of another network operation, just called repeatable network operation, which contains not only the type information I need for what I'm decoding from JSON, but also the fact that that type itself defines whether I need to repeat. And so this class itself is also repeatable because That's what the networking library needs. It needs an operation to repeat, and itself implements should repeat just by asking its generic type whether it should repeat. And so it's conformances all the way down here. And so now we can, in these few lines of code, define an operation that you write once, and now for any type that you'd want to be able to, say, poll against the back end for, all you need to do is define whether it should, under what conditions you should repeatedly get that type, and it will allow the operation to function automatically. So this entire class here, I cut some stuff out that isn't strictly relevant because it inherits from another thing, but is only a few, maybe 20 lines of code for an operation that can repeat indefinitely. And so it's really enabled a lot of flexibility by passing these types from the bottom to the top to enable you to, and this is something that came along much after I had already created the network operation. This is something I didn't know I needed right away. This repeatable feature was something that was added to the operations library while I was already building my app. So, it came up later on, oh, I can add this functionality to the types themselves. And since I'd already defined everything generically, all I needed to do was add a class that had another conformance. Another example of a protocol, this time one that uses associated types, is AlamoFire's response serializer type that I'd already mentioned. And as you can see here, it defines two associated types, serialized object and error object, which conforms to error type. And like I said, this allows the protocol to convey type information around to any user of this protocol. And so then the only other requirement of this protocol is that you have the serialized response method that returns a result that contains the serialized object and error object. Now, this allows us to convey the type information from this protocol down to the result itself without having to have specific methods or casting or anything like that to create the results, specific result instances that you need. This is all done, basically for free for you as you pass things up and down the stack. Another example is in the standard library is collection type. And collection type is one of the protocols that underlies things like arrays and sets. And this collection type conforms to other protocols, indexable and sequence type, and has an associated type called a generator. And this generator essentially lets you iterate through the values. I believe in Swift 3 this is going to be renamed iterator to more closely conform to other generic systems names for the same sort of idea. And it also gives you an associated type of a subsequence. So what is, of course, the subsequence of a collection is going to be very similar to a collection. It's going to be indexable. It's going to be sequence type. But each of the sequences is going to be a slice of the type of self. And so this allows you to build up these collections of just constraints on different things. And eventually, at the end, you can have an array or a set that inherits all of the functionality that you've defined in this protocol. Now, the protocols in Swift aren't quite as flexible as you would see in Objective-C, because really in Objective-C, all a protocol was a hint to the compiler that some object reference is going to have some set of methods. That's really all it was. It didn't actually define anything at runtime. It was really just, you were still just passing object pointers around, just like you were with any other type of object. It just let the compiler know that certain methods should be available. And collections of Swift protocols don't work like collections of Objective-C protocols. A Swift protocol, if you're trying to use it as a type in an array, is an actual thing that they allocate a certain amount of memory for and that they allocate the array for a certain size of. Whereas, like I said, for a collection of Objective-C protocols, that's really just a collection of object pointers that the compiler knows conform to a certain protocol. So it's an array like any other. Now, you can get some of this behavior back by marking the protocol at obc. This allows the Objective-C runtime to have knowledge of this protocol and sort of gives you the same behavior. But unless you really need a type, or unless you really need this behavior, you can gain a little bit of performance by not marking it like this. And of course, these do have, again, you're introducing a protocol that has, inherits from other protocols and must be, type checked against and things like that. So there is going to be a compile time and perhaps sometimes a runtime impact if you're using a protocol for something versus an actual concrete type. You can get some of this back by defining parameters that are generic, that are conform to protocols rather than just having a function that takes a protocol, because that way the compiler will know that you're maintain the full type information that comes into that function. And we'll see that the power of protocols really comes to the foreground when we talk about extensions. Now, extensions are pretty similar to Objective-C categories in that they can, and you get a little bit more power, but they have some of the same restrictions as well. But you can add computed and static and instance properties, just computed. You can't have stored properties. Static and instance methods, initializers, subscripts, nested types, and protocol conformance, which is one that's very convenient for breaking your code into different parts. In addition, you can extend any type in Swift, even types that in Objective-C you can't. So we can extend things like int, which can be very useful to do. And you can extend protocols, a feature added in Swift 2, to add default behaviors, which is something that the standard library has embraced heavily and is very useful in your own code for defining default behaviors that you want anything that conforms to a protocol to have. So for example, just simple extensions here, we can offer an extension on int that lets us set up a certain amount of memory. So we can say do things like set up an NSURL cache of 20 megabytes just by doing 20 megabytes. And that will return the multiplied out byte value for you, rather than having to say define the math in line or define some sort of constant somewhere that's just 20 times 1024 times 1024. Instead, you can extend int itself and say 20 megabytes, which is much more readable, and you don't have to store anything anywhere. You don't have to put a constant anywhere. You can also do the same thing to say transform units. Whereas in something like Objective-C, one of the common libraries that I've seen in Objective-C is essentially you take in a value that's usually an NS number or a double directly, and then it also takes in a unit from and a unit to, and it goes through and it finds whatever the transform is supposed to be for that and multiplies out the value, and you get an NS number back. But in Swift, you can extend double directly and just multiply that out yourself. And if you wanted to, you could break these multiplier constants out into their own values if you really needed to. But really, you can put them inline because they're only used in one place. And so you can offer things like feet and meters as just, whatever value you passed, 2 feet in meters, it's going to multiply 2 by 0.3048 and get an accurate number of meters back. And this gives you the ability to, if you find yourself transforming units a lot, just extend the base type that you're already probably expressing your values in. You're probably already expressing your unit values as doubles. You're probably already expressing the amount of memory that you might need for a URL cache as an int. And so instead of making some function that returns an int after multiplying it for you, you can extend that type directly and not have to worry about any additional, any function that has to live somewhere off in your code. This also makes it, extremely easy to test, because all your test is going to be, make sure that 1 mile in meters is 1609.344, and there you've then tested your entire unit conversion. Now, like I said, you can use extensions on protocols as default implementations. One of the things that the standard library likes to do, if you look at a lot of the functionality, is they'll have the base definition of, say, collection type, and then a whole bunch of extensions that provide different areas of functionality. One of these is, say, to get a lazy sequence type out of a collection type, all they do is offer an extension on collection type that returns a lazy collection of whatever self is. And self in a protocol is the type that has conformed to that protocol. So you can use it to, as we'll see in the future, you can use this information to constrain your extensions to only certain types. Which can be very powerful if you don't want bits of functionality to pop up on every type that conforms to this protocol. And so by extending collection type for whatever types you've already built, you can offer some pretty powerful functionality. Like, earlier I defined at least some of the functionality of a setting type, and I had this isSyncing property on setting. And so what if I have a collection of settings? Normally in Objective-C, like if I had a view controller that had an array of settings that I needed to display in a table view, maybe I would write a method in that view controller that would iterate through that for me and see if anything was syncing. That was something that happened pretty easily, and if you didn't pay attention too closely, it was fine because this was a really small function that you just added to your view controller. But what you can do in Swift instead is extend collection type, where the element of the generator is a setting. Array itself, you can't extend array and have its element be a concrete value type. It can be a reference type or a protocol, but you can't extend it for a value type, and that's really what Swift is all about, is maintaining those immutable value types around the system. And so by extending collection type instead, we get this functionality on array, but we also get it on set. And so now we have this free functionality on anything. And it also is perhaps a little bit easier to use. So say you have this array of setting type, or array of setting values, and just called settings in your view controller. All you need to do then is if settings.syncing, then you can do what you need to do if you have syncing settings. So rather than, say, calling a function that takes in this array and passes back a Boolean, it's much, it's a little more straightforward, and I think it's more readable here that you know exactly what's going on. Now, you can also, like I said, only extend protocols for certain types. And this gives you the ability to constrain where your extensions live, or where they're active, I guess. And so I had a protocol called keyboard did show observing. And this is really just a wrapper for, say, view controllers that needed to observe the keyboard. And it took and required you to implement a keyboard did show function that took a strongly typed notification that sort of took the information from the NS notification, pulled all the bits out of the info dictionary that comes with it, and puts it into a strongly typed thing. And I can then publicly extend, that protocol for anything that is a UI view controller. And so any view controller subclass will now inherit this functionality. So instead of having to do what I did down here, which is, observe keyboard did show notification with self and add the notification handler of the function that's defined in the protocol, I can just have a function that says observe keyboard did show notification. And that's what you would call in your view controller, say, view did appear. And it implements this functionality for you by default and allows you to sort of, limit it to UI view controller. And this gives you flexibility, again, for the future where, I have this protocol, but the ways that these default implementations are implemented would be different for different types of things that conform to it. If I wasn't using a view controller for this keyboard, I probably, maybe I don't want to call it this way, or for a different type of protocol, perhaps for view controllers I would implement something that would be visible to the user, whereas for other types it would only say, do the default implementation. We have some of the same extension limitations that you have from Objective-C where there's no stored properties. Again, this is something that might change with future versions of Swift, but it's hard to say right now. You can't have generic extensions, which is unfortunate. You can't say, you can't extend just array of string right now, and you can't define, if you wanted to, you can't define an extension, say, of string where you define some sort of generic type that you wanted to bring in. It's not possible to do that. You'd have to do something like define a protocol with an associated type, make string conform to that protocol, and then you can extend that protocol and have still access to that generic associated type. So it gets a little bit tricky that way. Again, some of these restrictions could be lifted in future versions of Swift. And there are areas in which the compiler doesn't like you to, like I said, make extensions of arrays of strings, because that makes a generic parameter non-generic, and so the compiler really doesn't like that. And so by extending the types and the protocols that you have and that the standard library has, you're able to build out functionality in ways that, as Apple platform developers, we never were before, and go beyond the type of top-down architecture that we see normally described. Because there have been a lot of movement, recently with things like reactive Cocoa or model view model, and just view models in general, where it's a lot of still the top-down stuff. You're looking down from what views you have, the view controllers you have, and seeing how you can organize them into nice little bits so that they're smaller and more testable, but it doesn't give you a glimpse of what the language itself can do for you. So we can look at some of this functionality in Xcode itself. Let me see if that's a little bit easier for people to have. So say if I have a typical value type of just person, first name, last name, age, and whether it's syncing to the back end. I make it decodable, so I know I can get it from JSON. This just returns a default value since we're not using this. It's just an example. I can then extend it to make it equatable. I have to provide an implementation for this because unfortunately Swift has no way to synthesize this for me, although for a type this simple it seems like it'd be very easy to. Hopefully that's a feature they add in the future. And then I also extended hashable just because that might be something we want to use in the future. So what we can do here though is do an extension on collection type where the generator element is a person. So now I can add functionality if I define an array of people. So if I do person and now I can put these values into an array and get some sort of functionality out of them. So say I wanted to define a derived property called, like we saw before, whether this entire collection of persons are syncing. And so I can say now is syncing. And we can see that the result of that is false because I've been able to pull that out of every value in the array just by running one line of code. And by extending collection type, this has also given us the functionality of being able to do this in a set. And so if I say set of Bill and Bob, I can also do is syncing. And this has given us the ability now to extend unique collections for our functionality. Now, if I wanted to say, we can already provide, the standard collection already provides us the ability to sort and things like that. But what if we needed to find something like, I don't know, the next highest age for some reason, or I didn't implement it here, next available database ID in case your backend requires you to send up database IDs for initializing new objects. So we could say first available age, it's just going to be an int. And really all we want to do here, this is going to be a little bit unsafe, but all we need to do here is say Because we're already in a collection, we can just automatically do stuff like map. We can map all of our ages. We can then sort from smallest to greatest. And then I can get the last value. And I'm going to, force it out, which isn't safe if you have an empty array. And then I can just say, +1. And now I can do down here, Bill and Bob dot first available age is 31. And so we've defined this functionality that's only relevant for this person type. And so now we can do that on all of our types. If we have multiple things coming back from the back end, some of them require some functionality, some of them don't. This gives us a good way to constrain all of our functionality to only those relevant types without having to define a lot of boilerplate. Whereas, if you wanted to generalize this type of functionality in something like Objective-C, you'd probably want to, make another protocol, have your type conform to that protocol. And even then, you weren't able to do much with that because you couldn't extend NSArray for functionality just for things of a type of protocol or something like that. I mean, you sort of could, but you had to do it manually, where you would loop through it and then dynamically check every time on the values to see if it's a certain type. So by embracing the generic functionality, embracing the protocols and the extensions that the language offers, you can build the language toward the problem domain that is being solved by your app, rather than having to build top-down functionality every time that you build something. And this gives you the flexibility and sometimes even performance and other benefits that allows you to, as you're building an app, add more and more functionality with almost zero cost to you. So that's my talk. This has been Exploiting Swift for Fun and Profit. I'm John Shire. Let's go back here. Some of the information that I got for this is from the book From Mathematics to Generic Programming by Stepanov and Rose, and then Advanced Swift by Eidhoff and Airspeed Velocity. Those are both. Advanced Swift is especially good, very useful. From Mathematics to Generic Programming is fairly esoteric unless you're really interested in the history of math and group algebra theory and how group algebra has helped define what generics are, because you can define generics as just, I believe, groups and semi-groups and things like that. And things like monoids, if you've heard of them, are actually from group algebra. So, any questions? Yes?
This is the second time I've heard the Swift language. Can you do you have any additional resources or tutorials to learn the syntax or practice the language?
Sure. The Apple Swift book that's available on the iBook store or just through their developer website is an excellent introduction to the Swift language. Really, all it requires you to know is what programming is, and it'll walk you through from the beginning of, oh, here's the int type in Swift. Strings, collections, things like that, all the way down to the end of defining, by the end of the book, it's defining the actual grammar of the language for you and things like that. So it's a pretty extensive and easy to read walkthrough of the entire language. Other than that, there are a lot of introductory tutorials online.
Stanford has a really nice class.
Oh, yes. Yeah, and Stanford had an iOS development course in Swift. I believe they call it CSP 193 or something like that. It's available through iTunes. And I think also directly from Stanford. That walks you through building iOS apps with Swift. I don't know how much of the base grammar or just language functionality they cover, or how far they go into things like generics. But it is at least a good introduction to building iOS apps with Swift.
And it's CS 193.
Oh, okay. Yeah. I knew there was a P in there somewhere. So. But yeah, the Apple book is very readable, much better than the Objective-C book that they had before. Any other questions? I have 1 minute left. We can ask more questions. No? All right.